You can see the colors that we can see are from on the spectrum from purple all the way to red, from 400 to 700 in wavelengths. And as you can see on this chart, that they are right between UV and infrared. We can do all of these, any type of vision application within these colors, within the visible spectrum of colors, but we can also do machine vision applications that require a UV or infrared source as well. Here's just another quick chart of light waves versus human images. You can see at the bottom what the human visible range is. And like I said, we can do UV and infrared applications, and we can also read UV and infrared barcodes as well. But we will, when we have these applications, we have to have some type of third-party lighting to make these applications successful. Here's my last chart on light waves. Your human versus your light sources. You can tell at the bottom your human visible range, and on the left is your relative intensity. And this is just kind of everything that the humans see, what we can see. So we use different types of illumination when we're doing machine vision. We have LED, fluorescent, halogen, xenon, and laser. One that you never want to use, is never recommended to use, is ambient room light. That's not recommended because ambient light typically is always changing. And with ambient light, you can never have repeatable success. With third-party lighting, exterior lighting, you can have much more and greater success with that. Ambient lighting is never recommended, and we're going to go over some of that here shortly. So this is a few different ways of how lighting reacts with objects. Each object that we come across for machine vision is different. And these are just a few examples of how a light or how your third-party lighting can interact with the object that you're inspecting. It can absorb, it can reflect, it can have transmission through your object, it can scatter, or also can have emission. And any type of object that you're performing inspections on can be different. You can have different types in the same facility. So here's some common illumination techniques, and this is also kind of showing how light interacts as well with objects. You have a bright field lighting technique, and you can see that light bounces back up into the camera. A dark field lighting technique, the light rays go away from the camera. Backlighting, the light is placed behind the object you're inspecting. Diffuse dome, you have a dome, it really looks like a dome, and lighting is scattered in around the dome off the object, and the camera looks at the object, and actually with this can kind of give side views of the object as well. You have structured light with the laser above, and you have a coaxial lighting technique. So here's an image of bright field lighting versus dark field. You can have a bright field looking down at an object you're inspecting, and you can see kind of how that lighting technique will bounce back up into the lens of the camera, while on the other hand, a dark field zone is going to reflect the light away from the camera. So when we do machine vision applications, we test the object with many types of lighting, and different types of lighting will give you different results on the object that you're looking at. On this slide right here, we have a bright field and a dark field. Now these are the same cameras with the same objects that we're looking for, but we're just using a different lighting technique. You can see on the left-hand side that the image via the bright field ring light, you can't really see anything. You can see the light, but you can't see the object. In the dark field ring light, you can find a scratch in the mirror, and these are just trying to show how different types of lighting techniques come across on objects that you're inspecting. Once again, we have the same camera, the same object we're inspecting, but we're just using a different type of light. On the left-hand side, we're looking at a bright field ring light. and on the right hand side, a dark field ring light. And you can see above each image how the lights look different and how the LEDs are formed around them differently. But not only that, you can tell just by looking at the object how much cleaner of an image the dark field ring light gives on this object. Backlighting. So we have a picture here of a light bulb, same camera, just two different types of lighting techniques. We have a bright field ring light on the left, and then we have just a backlight on the right. And you can tell how much of a different image you can get on this light bulb. Now, depending on what you're looking for and what you're inspecting, will kind of determine which way you'll go with what type of third-party lighting you'll use on this application. On backlighting, it is typically used a lot, typically because backlighting doesn't have to be so accurate. Backlighting does have a fuzzy edge on some of the parts. This can lead to poor measurements, but like I said, a lot of times backlighting is not used for measurements. It's kind of just used for presence absence. Here's an example of diffuse dome versus a bright field ring light. On the left, diffuse dome is on the right. This is looking at a can of paint, same camera, just different lighting techniques. And here's the coaxial. So coaxial is not used, but on certain applications. So the surfaces are perpendicular to the light source that reflect the light. The other lighting sources scatter light, but this one surface is perpendicular to the light source. It's used on reflective, shiny surfaces, and the key to getting the coaxial lighting to work is the beam splitter glass. And you can tell on the diagram of the drawing of how that beam splitter is working and how it kind of reflects the light. Okay, now we're going to go a little bit over a color inspection versus a grayscale camera inspection. Color cameras are not used a lot, but sometimes they are just because they have to be, and they're requested to be. So this is just a little bit of understanding about the color wheel. So when you want to darken a particular feature, you use the opposite color of lighting. So a green light makes the red a darker feature. When you want to lighting a particular feature, use the same color of light. So a red light will make a red feature look light. So if you have a red light shining on a red object, you may not even see the object in your machine vision camera because it's going to wash away the object and everything is going to be almost white, kind of like looking into a light bulb. You're not going to be able to see anything. Just note that the monochromatic light are using the same color filters that work the same. The red light does the same thing as a white light would with the red filter. Color images contain 24 bits of information per pixel, giving a colored camera more pixel depth than 8-bit imagers. Most color cameras use so they have a grayscale imager, but they have a Bayer filter put in the camera. On these, each pixel on the CCD, that's the image sensor, has its own filter. In the Bayer filter, you have half of the resolution is going to be green, 1/4 is going to be red, and 1/4 is going to be blue. So by using this interpolation with the demos and the algorithms, the RGB information per pixel position can be calculated based on the neighbor pixels. So like I said earlier, when you're using a color camera, you're going to lose resolution and also speed, but sometimes color cameras they just have to be used to solve some types of applications. We love to solve applications if we can with a monochrome camera, just for some of these reasons. And this is just a quick little slide of talking about how a color camera uses a trichroic prism. And what this does is just split the light beams into red, green, and blue light. It's just kind of showing how the Bayer filter and the prism work together to get the higher quality image comes to a color camera in high resolution. Color inspection with a color camera Color imager determines the color of a pixel by interpreting the intensity passing through a grid of 2 by 2 pixels. This is using Bayer filter, so it's going to be a monochrome camera with a Bayer filter. So you can see on the left, the imager without the filter. This is what the starburst look like. When you put on the Bayer filter in the monochrome camera, this is what it's going to generate. So this is a vision application. On the left-hand side, you can see the color image. It is being performed by a color camera with the Bayer filter with a third-party white light on it. So you're getting a good image of the colors of the starburst. Then you can also, we take the same image and we put a monochrome light on this, and then we put a grayscale camera, and you can tell by, so we took this image and did 5 different shots of this with 5 different lighting, different types of color lights. So as you can see, when you take a grayscale camera, you put a red light, a green light, a blue light. We took one with a red and green, and then a white light. You can just tell by each of these how much a different color of light can make in the different colors of the starburst in your monochrome camera. This is kind of emphasizing how important third-party lighting is. It's emphasizing how important it is to choose the correct type of lighting, the correct type of color of your third-party light, just because if you pick the wrong color of lighting, then you can get a lot of images and a lot of things that look the exact same, when in reality, if you take a look at the color camera on the left, you can tell that we clearly have 4 different types of starbursts in this image. But if you choose the wrong lighting with the monochrome, a black and white camera, you can tell all the different types of images that we can get with different types of third-party lighting. So sometimes we will use a color filters. These are used on monochrome, the black and white cameras, and really they have some features to them. So sometimes if you don't fully need a color camera or the Bayer filter, we can get away with using these bandpass filters. But what they do is they enhance the contrast for view. They're designed and used with all the common LEDs used in machine vision lighting, designed for to use with laser diodes and UV, excited fluorescent emissions, shield systems from the variability of unwanted ambient lighting for UV, invisible, and near infrared wavelengths, and they're essential for imaging the UV and near infrared. So like I said earlier, we can do these UV and infrared applications if you have any. But when we come across these applications, we have to use either these bandpass filters or some type of third-party lighting to be able to detect the infrared or UV applications. Here's an image. The one on the left-hand side is an image that's just using ambient light that has no type of filter, no type of third-party external lighting. But the image on the right has the bandpass filter on it and has a third-party light as well. And you can see the difference in the image, in the details that we can get just by adding a filter and a third-party light. A polarized filter, the one thing when people want to talk about polarizing filters, the one common thing you can always make a comparison to is sunglasses. If you put a pair of sunglasses on that's non-polarized and put a pair of sunglasses on that are polarized, you can definitely tell the difference when you're looking at objects. What they do is they reduce unwanted reflection or specular glare that can be used to check stress patterns in transparent glass or plastics. For smooth surfaces that are covered with grease or oil or liquid, to achieve the best results by using a polarizing filter over the lens in conjunction with the polarizing film or polarizing glass sheet and light source. Most polarizers are wavelength range specific, visible or infrared polarizing filters or filter sheet materials that are offered. They're often used on images non-metallic surfaces that will produce a polarized light and reflection. Therefore, that uses linear polarizers that can often result in the benefit of industrial imaging applications. So polarizing filters have actually become some of the most popular filters that we come across, not only in machine vision, but also when we do barcoding as well. As you can see, the image on the left, that has no type of polarizing filter. It's just looking at a light socket wrapped up in plastic, probably before like a checkout. You're getting ready to purchase it, but you can tell the difference in the details in the image when you just add a polarizing filter to the camera. You can tell the difference in the more details you get in the image.